So last time we were discussing the Gibbs entropy, right? The Gibbs formula for entropy. And we said that everything in the canonical ensemble can be expressed in terms of the partition function. So let's see what we can do to re-express the Gibbs entropy in terms of the partition function of the canonical ensemble, right? So the Gibbs entropy formula is a very nice formula, and that's because it's got probability built into it. And this is the expression that can be generalized to quantum mechanics. And when we go and do examples in the near future, we shall see how this is generalized in quantum mechanics. This is also the expression that can be generalized in information theory, right? So of course, the KB is replaced there. It's not the right constant to use in those cases, but in information theory, there is also an analogous idea of entropy. So, so what we now do is that we use the fact that we know what the Boltzmann, what the expression for P of alpha is. So P of alpha is given by e to the power minus beta E alpha, right? Divided by Z, where Z is the partition function. So beta, let me remind you, is the inverse temperature in terms of KB. So beta is 1 over KBT, KB being the Boltzmann constant. So now if I insert this into these guys, what do we get? We get S is equal to minus KB, and there's a sum. And then from the first term, we get, because of P, we get minus B eta alpha divided by Z. And from the first term, we get minus beta E of alpha, right? This comes from the log. So, right? So inside the log, we have this guy, but we have this guy, but we also have Z. So the Z is going to be because it's inside the log, we get a different term here, which is log of Z, right? So we get these two terms. So we could write out these two terms, and the first term, there are two minus signs, so we get K of B, and then sum over alpha e to the power minus A alpha, well, there's a beta here, divided by Z times B of E of alpha. Now the second term is multiplying minus minus, gives me plus, and then we have K of B, and what we have essentially is the sum over all the probabilities. So that gives me 1. So the second term just becomes KB log of Z, okay? And the first term, you can write this as K of B sum over alpha. Now you can put the beta in front over here and then divided by Z, and then we can have d by d beta acting on e to the power minus beta E alpha, but there's a minus sign here, so we put a minus sign over here. So this is what happens to the first term. So this derivative brings down a factor of minus E alpha. This minus cancels this minus. This E alpha becomes this E alpha. And this beta is this beta. So we get to the second term remains the same. And then, you can just verify that with our definition of beta, this is a parenthetical remark, is equals to kBt means that t times d by dt is equal to minus beta times d by d beta. Okay, so if I do this, then I can replace the beta derivative by a t derivative, and because of the minus sign, what I get is kb sum over alpha t by z d by dt e to the power minus e to the power alpha divided by kbt plus kb log of z, right? And this is easy to see now. This is S is nothing but kb d by dt times t times log of z. So we have a very simple expression for the Gibbs entropy in terms of the partition function. Okay. Was there any question about the derivation? I just leave this as an exercise for you to do.
Sir, the part where you put 1 in the total probability, you didn't
Right.
put 1 on the first term. Can I know
No, I
why?
didn't because it was weighted by this thing. So the sum over alpha is not just the sum over this thing, but it's this thing times this thing. So this is not 1.
Sir, I'm not exactly sure about the parenthetical remark, like the beta.
Sure, I can
Partition.
derive that. So here is beta is 1 over kbt, right? So that means that if I take the derivative with respect to t, I can write this as del beta by del t, del by del beta, right? Now, what is del beta by del t? Well, we have a 1 over kb, and then we have minus 1 over t squared, right? This is what we get if I take the derivative of 1 over t. And then I have d by d beta, del beta, right? And then I can write this as d by d beta, and then minus kb t squared d by dt, and then we get, so what I can do is I can keep 1t here and take a factor of kbt to the other side, and that gives me a factor of beta, and on this side I get t del by del t. Okay.
I see. There was something like this that we had to do in the tutorial. I was really confused. Yeah.
It's
Okay.
all right. Yeah. It's these. Yeah, I also find these things confusing.
So would you scroll up a bit?
Yeah.
The S equation, the
This
red
one.
rectangle, yes.
Yes.
What is the advantage of the Gibbs entropy? I mean, why did we derive this S?
Right, because I'm fulfilling a promise, and the promise I'm fulfilling is that is the following. I made a statement that every quantity of the canonical ensemble can be derived from the partition function z. Right. So I'm just saying that this is the expression for the partition for the entropy from the in terms of the partition function. Okay.
Yes, sir.
Suppose you're just calculating. Yeah. So that's it. It's just a different way of looking at the same thing. All right. Okay, so
this
before we
equation is
move,
basically telling us how we can get entropy from the partition function.
yeah, exactly. Because when we derived the entropy Gibbs formula, we used very probabilistic argument, right? So we got an expression in terms of probability. So I'm just connecting that to the partition function now. That's it.